Episode 2. When stormwater overwhelms the sewer network. When a city floods during an intense storm, the visible water is only the last frame of a much longer engineering story. Rain has already moved across roofs, streets, gutters, inlets, private laterals, open channels, detention basins, pump stations, and sometimes wastewater pipes. By the time water reaches a low intersection, a basement, or a manhole cover, the network has answered a simple question. Can every part of the system move, store, infiltrate, or safely overflow the water arriving at that moment? If the answer is no, flooding begins. This episode asks one engineering question. Why do urban drainage and sewer systems flood during intense storms? And which interventions address the bottleneck? We will follow the storm from the catchment surface to the pipe network, through capacity limits, backwater, surcharging, combined sewer overflows, green infrastructure, storage, conveyance, operations, and field investigation. The promise is practical. By the end, a flood will look less like a mystery and more like a set of linked constraints. First, the documented facts. In the United States, the Environmental Protection Agency explains that some communities have combined sewer systems, where stormwater runoff, domestic sewage, and industrial wastewater are collected in the same pipe. During wet weather, flows can exceed the capacity of the system and discharge as combined sewer overflows, or CSOs. The EPA also describes green infrastructure as practices that use vegetation, soils, and natural processes to manage water and create healthier urban environments, including rain gardens, planter boxes, green roofs, and permeable pavements. The national academies describe urban flooding as flooding that occurs when stormwater inflow exceeds the capacity of local drainage systems to infiltrate, store, or convey water, and they highlight the roles of topography, land development, and undersized or constrained systems. Now, the episode assumptions. We will show a simplified urban catchment with roofs, roads, yards, inlets, storm pipes, sanitary sewers, a possible combined sewer district, storage facilities, and an outfall. It is not a real city, and it is not a design model. It is a teaching diagram. When we show a hydrograph, pipe profile, or storage volume, the values are illustrative only, unless clearly identified as source-based. The point is the mechanism, not a universal design number. Start with the catchment. Rain falls on a surface. Some water is intercepted by leaves or depressions. Some infiltrates into soil. Some evaporates later. The remainder becomes runoff. In a forested or lightly developed area, more rainfall may be slowed by vegetation, surface roughness, and soil storage. In a dense urban district, roofs, asphalt, compacted soil, and connected drainage surfaces often deliver water faster to the network. The same storm depth can produce a sharper and earlier runoff peak when the catchment is highly connected. That timing matters. Flooding is rarely caused by total rainfall alone. It is caused by rainfall intensity, duration, spatial pattern, antecedent wetness, surface condition, inlet condition, pipe capacity, downstream water level, pump operation, storage availability, and maintenance state, all interacting over time. A short, intense burst can overwhelm inlets even if the total storm depth is modest. A long storm can fill storage and raise downstream water levels. A coastal storm can block an outfall even before local rainfall peaks. A snowmelt event or saturated soil can reduce infiltration before the storm begins. The first bottleneck may be above ground. If gutter flow cannot reach an inlet, or if the inlet is blocked by leaves, sediment, trash, construction debris, or parked vehicles, the pipe capacity below may not matter. Water ponds in the street because the entrance capacity is lower than the arriving flow. This is why field observations during and after storms are so valuable. High water marks, debris lines, inlet blockages, and flow directions can reveal whether the flood began at the surface, in the pipe, or downstream.
The second bottleneck is conveyance. Pipes and open channels move water with a finite hydraulic capacity. Their capacity depends on slope, roughness, diameter or shape, sediment, structural condition, entrance and exit losses, and downstream water level. If inflow exceeds what a reach can convey, the hydraulic grade line rises. In a closed pipe network, that can mean surcharge. The pipe flows full and pressure increases. If the pressure grade rises above the rim of a manhole, inlet, basement connection, or other opening, water can escape or back up. The third bottleneck is downstream control. A pipe may be large enough in isolation, But if the receiving river, tide, lake, canal, or larger interceptor is high, the outlet loses driving head. The system becomes tailwater limited. Backwater can move upstream, reducing capacity reach by reach. Urban flooding is therefore not only a local pipe size problem, it can be a network problem, a watershed problem, and sometimes a coastal or riverine boundary problem. In combined sewer areas, the stormwater and wastewater question becomes more sensitive. The U.S. Environmental Protection Agency's combined sewer overflow discussion is jurisdiction-specific to U.S. regulatory programs, but the physical concept is broadly useful. One pipe carries both sewage and runoff. During dry weather, flow goes to treatment. During wet weather, the combined flow can exceed the system capacity, and designed overflow points may discharge to prevent widespread backups. This is a public health and water quality concern, not just a hydraulic inconvenience. Separate sanitary sewer systems can also experience wet weather stress. They are not intended to carry stormwater, but inflow and infiltration can enter through illegal connections, roof drains, foundation drains, broken pipes, leaky joints, manholes, and saturated soil. During intense storms, that extra water can consume capacity in pipes, lift stations, and treatment plants. The visible symptom may look similar: manhole surcharging, basement backups, or bypass risk. The root cause, however, is different from a combined sewer overflow and needs different investigation. So, which interventions address the bottleneck? The first rule is to locate the limiting mechanism before choosing the solution. If flooding starts because water cannot enter the drainage system, adding downstream storage may not fix the street. If the pipe is undersized, cleaning inlets alone may not solve it. If the outfall is tide-locked, upsizing an upstream pipe may move water faster into a closed door. A good intervention matches the bottleneck: reduce inflow, slow runoff, increase storage, increase conveyance, remove obstructions, improve operations, or provide a safe overflow pathway. Reducing inflow begins where rain lands. The Environmental Protection Agency describes green infrastructure as managing stormwater at or near its source using vegetation, soils, and natural processes. Rain gardens can receive roof or sidewalk runoff. Planter boxes can intercept runoff in tight urban rights-of-way. Green roofs can slow roof runoff. Permeable pavements can allow water to pass through a surface into a storage layer when designed and maintained for the site conditions. These measures are not magic sponges. They have finite storage, soil constraints, maintenance needs, and performance limits during extreme storms. Storage is the next family of interventions. Detention basins, underground tanks, oversized pipes, tunnels, parking lot storage, blue roofs, and controlled surface storage all shift timing. They do not eliminate water, they hold it and release it later. Storage helps most when the problem is peak flow arriving faster than the downstream system can accept it. But storage can fail as a strategy if it is already full, if the outlet control is poorly matched, if sediment reduces volume, if groundwater limits construction, or if a downstream boundary remains high for too long. Conveyance interventions increase the system's ability to move water. They include larger pipes, relief sewers, parallel channels, culvert improvements, pump stations, inlet upgrades, open channel restoration, and removal of hydraulic restrictions. These projects can be powerful, but they can also transfer risk downstream if not evaluated at the system scale. Moving water faster from one neighborhood may raise the peak somewhere else. Conveyance upgrades require hydraulic modeling, field verification, and coordination with receiving waters and downstream assets. Operational interventions often receive less attention than capital projects, but they matter. Cleaning inlets, removing sediment, inspecting flap gates, maintaining pumps, confirming sensor reliability, exercising valves, updating emergency procedures, and coordinating road closures can reduce the chance that a small defect becomes a flood. Operations cannot make an undersized system unlimited, but they can protect the capacity that already exists.
Green infrastructure, storage, and conveyance are not competing slogans. They are tools at different locations in the hydrograph. Source controls flatten the early response and reduce connected impervious runoff. Distributed storage delays and attenuates peaks. Major storage captures excess volume at strategic points.
Conveyance improvements reduce losses along the path. Controls, sensors, and maintenance keep the intended behavior closer to reality. The best solution is often a portfolio, not a single measure. There are also risks and trade-offs. A permeable pavement clogged by sediment may lose function. A rain garden placed in unsuitable soil may hold water longer than intended. A detention basin without safe overflow routing may create a new hazard. A pump station without backup power may fail during the same storm that needs it most. A larger pipe may increase downstream peak flow. A combined sewer control project may reduce overflow frequency, but still require long-term inspection, maintenance, and adaptive management. None of these are reasons to do nothing. They are reasons to design with failure modes visible. Equity and access also matter. The national academies emphasize that urban flooding is shaped not only by pipes and rainfall, but also by land development, local conditions, information, and decision-making. Neighborhoods with older infrastructure, flatter topography, limited tree canopy, more pavement, or fewer resources for recovery may experience repeated harm. Engineering analysis should therefore include field evidence, resident reports, historical maintenance records, and social vulnerability, while keeping evidence, assumptions, and recommendations clearly separated. A practical checklist starts before the storm. Define the drainage area. Map overland flow paths, inlets, pipes, manholes, outfalls, pumps, storage, and low buildings. Identify whether the area is served by separate storm sewer, separate sanitary sewer, combined sewer, open drainage, or a mix. Confirm downstream controls: river stage, tide, canal level, detention outlet, treatment plant interceptor, or pump discharge condition. Then assemble rainfall, water level, complaint, maintenance, and inspection records. During or soon after a storm, observe the sequence. Did water bypass inlets? Were inlets blocked? Did manholes surcharge before street ponding? Did basements back up without street flooding? Did outfalls submerge? Did pumps run? Were alarms active? Did the flood peak match the rainfall peak or lag behind it? Each answer points toward a mechanism. Photographs, timestamps, high watermarks, and resident observations are engineering data when they are documented carefully. For diagnosis, build a simple cause chain before proposing work. Rainfall generated runoff. Runoff reached inlets. Inlets accepted or rejected flow. Pipes conveyed or surcharged. Storage filled or remained available. Outfalls discharged or were blocked by tailwater. Wastewater pipes stayed separate or received inflow and infiltration. The flood occurred when one or more links could not pass the arriving water. Then test interventions against that link: source reduction, inlet improvement, pipe rehabilitation, storage, control, pump reliability, overflow routing, or land use change. For design and planning, avoid universal promises. Do not say that one green infrastructure feature will solve all intense storms. Do not say that a larger pipe is always better. Do not compare alternatives only by construction cost if the episode or study has not documented life cycle maintenance, land, energy, water quality, safety, and downstream impacts. Use local design standards, monitor data, hydraulic models, public health requirements, environmental permits, and community priorities. Where U.S. EPA sources are used, identify them as U.S. references, unless the physical principle is clearly general. The central lesson is this: stormwater flooding is a capacity and timing problem across a connected urban system. The bottleneck may be a curb inlet, a pipe breach, a combined sewer regulator, a pump station, a storage outlet, a maintenance defect, a maintenance river, or the landscape itself. The right intervention is the one that changes the limiting part of the response without hiding risk somewhere else. When the next intense storm arrives, the city will again run the experiment in real time. Rain will become one-off. One-off will seek a path. The drainage and sewer networks will fill, store, release, or overflow. Our job is to understand the chain before the water reaches the doorstep. Map it, measure it, maintain it, model it, and choose interventions that match the bottleneck. That is how an overwhelming flood becomes an engineering problem we can investigate, communicate, and reduce.